Hi all, in today's video we would like to discuss double integral average value. Now double integral average value is something that's kind of important, so it's really used in the real world with approximation methods, so like a Riemann sum. You can think about contour plots like this, so you could think about what's the average height of a mountain. You get a contour plot. Obviously the mountain's not going to be modeled by a function. It has its own topology that's geologic and not mathematical, but you can find the average value of that using your double Riemann sum, however into it you want to get. But it's good to go through the motions here because sometimes you are going to need to find the average value. It's very simple, very similar to the single variable average value, just a little bit more complicated, and I'll also take the time to kind of go through more complicated double integral in this video, which will have some U substitutions in it. And just remember that in this course I'm not going to go through super challenging integrals, but just know that like trigonometric substitution, partial fractions, integration by parts, they're all still on the table for Calculus 3 tests. So here's the prelude, and we'll kind of cover this with a single variable average value here, but then we'll just move it to double integral. Basically, if I want to find the average value of a function f, then I take 1 over b minus a, the difference of the endpoints, times the integral between a and b of f of x dx. So now if I want to do this for a double integral, I can take the average value by taking 1 over the area of my region. And now the region, right now, we're dealing with rectangular regions described by Cartesian products, but this could be any area that you're integrating over, times the double integral over the region of f of x and y with respect to the differential area. So let's try an example here. I would like us to find the average value over f of xy equals e to the y times the square root of x plus e to the y over the Cartesian product of r is equal to 0, 4 times 0, 1. So now we need to determine our delta A. So our area is going to be the rectangle. So the rectangle is swept out on the x by 0 to 4, and the y is swept out by 0 to 1. So we get kind of a rectangle that looks kind of like this. We find the area of that. Area is base times width, delta x times delta y. We get 4 times 1, which is equal to 4. So if I want 1 over area, then that's going to be equal to 1/4, right? So now, let's actually start evaluating our integral. So I think with Fubini's theorem, the idea here is you're going to integrate with respect to whichever variable is going to give you the easier second integral. So we're going to integrate with respect to y first, because that's got the most complicated thing. If we get the most complicated thing out of the way, then it's going to be nice. So we get f bar is equal to 1/4 times the integral between 0 and 1, then the integral between 0 and 4 of e to the y times x plus e to the y dy dx. So now what we do to evaluate this is we can set u equal to e to the y plus x. And when I differentiate, I just get e to the y. So that's a perfect U substitution. So we get, if we evaluate the fundamental theorem of calculus after that, we get 1/4 times the integral between 0 and 4 of x plus e. Oh, sorry. Did I get these bounds wrong? I think we're doing this one first. Oops, so we're going the integral between 0 and 4, and then here we're going between 0 and 1. So we get 2/3 times x plus e to the 3/2 minus 2/3 x plus 1 to the 3/2 dx. So now we're going to break this integrand into two parts. The first is going to be I sub 1 of x. We're going to take this guy first. So we get the integral between 0 and 4, 2/3 x plus e to the 3/2 dx. Now we're going to set u equal to x plus e, and then we get 4/15 times 4 plus e quantity to the 5/2 minus e to the 5/2. Okay, now we can do the second one. We get I2 of x is equal to negative integral between 0 and 4, 2/3 x plus 1 to the 3/2 dx. Set v equal to x plus 1. We get a final answer of 4/15 minus 20 over root 5 over 3. Okay, So now the average value of our function is going to be 1/4 times I sub 1 of x plus I sub 2 of x. So we get that's equal to 1/4 times 4/15 minus 20 rad 5 over 3 plus 4 plus e to the 5/2 minus e to the 5/2. And that's our final answer. You can kind of see what the function looks like here on our interval. We can examine what that actually is. All right, in the next video, we are going to introduce double integrals over general regions using Cartesian coordinates. So there's actually two ways we can do double integrals. We can do the method with Cartesian coordinates. We can also do the method with polar coordinates. Sometimes one is easier than the other. So we'll cover that in the next video. We'll see you then.